Earlier, we were talking about surface area, and recently we've been talking more about parametric equations, and now what we want to do is combine both of them. So I have these parametric equations here that describe a curve, and we're interested in t from 0 to 3, and what we want to do is take that curve and rotate it about the x-axis and find the surface area of that. So using what we've learned with both of those concepts, why don't you pause the video and give that a try on your own? All right, assuming that you've given it a go, let's start doing this. And I think a good first thing to do is remind ourselves about surface area. Okay, so if we just have a random curve, Now, one thing that we learned a few videos ago, maybe I'll bring that up, we could take these parametric equations and put them into, we could construct a rectangular equation from them. We saw how to do that, but in this case, I want to show you, you don't need to. In fact, I just want to give us a random curve here and talk about, what happens when we rotate a curve around the x-axis and how we find the surface area of that. Let's remind ourselves. So if we just have this random curve, maybe it looks something like this. Okay, something like this. This is a random curve. And what happens when we rotate it around this x-axis? So when we rotate it around this x-axis, what do we get? We get something that looks maybe like that. Okay, and maybe we're interested in only a little interval of it. And what we need to see is we're going to get a vertical slice. That looks something like this. Okay, we get this vertical slice. And what we did when we were talking about surface area is we pulled this vertical slice out. We said, okay, here's our slice. This is a circle, and it has a radius. It has a radius like this here. Pull a radius on here. That is not a pretty slice that I took. Something like that. Okay. And we said, now that we have this, we want to end up getting to defining what these little pieces of surface area are. And we want to throw those in an integral and sum them up, and then we'll have the full surface area. And we said, when we pull these vertical slices out, we don't want to find the area of these circles, but instead we want to find the circumference of them. So that is 2 pi r. And then we multiply that by a little piece of arc length. That's what we were talking about when we were talking about surface area. So a little piece of arc length here. And when we multiply these together, that gives us this little piece of surface area. So that's a review from earlier. Now, how do we start to talk about, okay, we have these parametric equations up here. How do we handle those in terms of this down here? And what we need to do is remember, okay, when we're rotating around this x-axis here, r is going to be y. So we can write that out, 2 pi r. So r is now y, and then we're still multiplying by ds. And what we said when we were talking about surface area and setting up these integrals is, hey, we're rotating around the x-axis, so r is y, but now how we represent y can change based on how we want to integrate. And in this case, we're going to show that we can integrate with respect to t. And therefore, we're going to represent y in terms of t. And all we need to do is look up at our parametric equations to do so. So we see that y is equal to 2t squared plus 5. So we can write that out. That's now going to be 2 pi. And we're saying that y in terms of t is going to be 2t squared plus 5. And this right here is the circumference of these vertical slices that we're making. And now, what we've seen in the last couple videos is ds. Mainly, if we're going to integrate with respect to t, we need to get ds in terms of dt. And we saw that in the last couple videos that we could represent this little piece of arc length as the square root of dx dt squared plus dy dt squared, and then dt. We saw this in the last couple videos. Now, let's solve this. We have these parametric equations. All we need to do is take the derivatives of them. Let me grab these parametric equations real quick. Copy paste these guys, and we'll get to work on them. All right. Copy, and then we'll paste these guys down here. Awesome. There we go. All right. Now, we need to find their derivatives with respect to t. let's do that. Let's get dx dt going. So derivative of x with respect to t, that's just going to be 6t, and then dy dt. dy dt looks like we have 4t. Throwing this in, what do we get? We get ds is equal to the square root of, we found dx dt to be 6t, so that's 6t squared plus 4t squared. And then we still have dt. Now let's see if we can simplify this guy. Let's see how far we can go with it. So we're going to have, this is 36t squared plus 16t squared. What is 36 plus 16? That is 52. So that's going to be 52 t squared dt. And we can rewrite this as the square root of 52 t dt. And then can we break down 52 anymore? Let's see. Divide it by 2 maybe, 26 and then 13. Yep. So we can rewrite this as 2 times the square root of 13 t dt. That is what we have for ds. And now we're going to take that and throw that into what we had. So let's see if we can remember that. 2 times the square root of 13 t dt. So this is 2 times the square root of 13 t dt. And then we'll fill in what we had earlier for these circumference of these vertical slices. So that's 2 pi times 2t squared plus 5. Now, all of this right here represents these tiny pieces of surface area. And finally, we can throw together a definite integral. So let's throw together a definite integral now and finish this guy off. So we're going to have the definite integral, and we'll throw limits of integration on in a little bit, but we're just going to throw all of this guy into here. So this is going to be 2 pi times 2t squared plus 5, and then times 2 times the square root of 13t dt. And then if we're integrating with respect to t, what are our limits of integration? Well, we were told those in the directions. Look at that right there. We're interested in t from 0 to 3. So we got 0 to 3 as our limits of integration. This right here is our definite integral. And now all we need to do is solve it. So let's see. We have a few constants that it looks like we can pull out. And we got this 2, this pi, 2, and a square root of 13. So we can take that all out. That's going to be 4 pi, it looks like, times the square root of 13 times this definite integral from 0 to 3. And then we're left with 2t squared plus 5 times t dt. And we're getting closer. Let's distribute that t. Let's see what we get. I'm going to grab some space. We've got a lot of yellow going on. Maybe should have chose a different color. All right, let's distribute that t, and we're going to get this. 4 pi times the square root of 13 times the definite integral from 0 to 3. And now we're going to have 2t cubed plus 5t, and then integrating this with respect to t. And finally, let's anti-differentiate and evaluate and see what this answer is. So it looks like we're going to have 1/2 t to the 4th power plus 5 over 2 t squared. And then this is going to be evaluated at 0 and 3. What does this come out to? And we have this guy coming down. This is 3 to the 4th power. That is 81. So we have 81 over 4. And then we have plus, let's see here, 9 times 5, 45. 45 over 2. And let's see here. Oh, I wrote a 4. I wanted that to be a 2. This should be a 2. Let's see. 3 to the 4th power, 81, and then over 2. Over 2. There we go. And then evaluating that at 0, everything just becomes 0. And we still have this piece right here. 4 pi times the square root of 13. Here we go. This is it. Let's take out this 1/2 from these terms here. And we'll be left with 2 pi times the square root of 13. And then 81 plus 45 is 126, it looks like. And then times 2, that is 252. So boom, 252 times the square root of 13 times pi. That is our surface area right here. And we are done. And what I wanted you to see is, hey, we already learned how to compute surface area using integrals. So nothing new was there. But all we did was introduce that, hey, we could also compute that when we have some parametric equations. We could integrate with respect to t. So I wanted to show you that you could do that as well.